So what I was going to do is just do some practice problems that are in the sections that are being covered on the test. And so these will be different than the ones you've seen before, so you can practice some new stuff. And they'll also be different from the ones that are on the sample test. So that way you can practice the sample test and have even more examples. A lot of variety of problems to practice on. So this is going to cover, like normally what I would probably do today would be give problems that are based on all that stuff we did on Wednesday, all that new material. But because we have the test, I'm going to go backwards and cover some examples of the older stuff. And then we'll worry about the stuff we learned on Wednesday later. Okay. So let's, we're just going to throw a bunch of problems up here. This is not going to be in any particular order. I haven't actually typed this up yet. So I was a little behind on getting that done. I'm going to type all of these up, and then I will post the questions and the answers to this hopefully by tomorrow. I'll try to get that done, okay? So let's try this one. So these are just some practice problems. And let's try this one first. So number one, okay, so if the limit as x approaches infinity of f of x is equal to L1, and the limit as x approaches infinity of g of x is equal to L2, then prove that the limit as x approaches infinity of f of x plus g of x is equal to L1 plus L2. When you look at that problem, you might feel like you saw this before. Because this was one of the properties of limits that we talked about before. However, we never actually proved this one. This is for infinity here. Infinity, infinity. So the one that we did in class was limit as x approaches c. Right? So I'm doing this one here. By the way, if I'm doing it here, you can use it. After anything that has actually come out of my mouth, you can use. So this is fair game in the future. If it ever shows up as something relevant to use, you can use it. Okay? So probably if this was like on a test, this would be a very nice test question, but probably the first part, there would be a part preceding this, which would be to just write down what the definition of the limit of f of x equals L1 is. So let's start with that, just so we know what we're working with here. So the limit as x approaches infinity of f of x equals L means, do you guys remember the definition?
For epsilon greater than 0.
Okay, for all epsilon greater than 0.
There exists a alpha.
There exists an alpha greater than 0, right? Such that
if x is greater than alpha,
if x is greater than alpha,
then f of x minus L, the absolute value of that is than epsilon.
There we go. Okay, perfect. So that's like the first part of it. And this is going to be easy free points to get if you just write down the definition first. Okay? So that's the definition. So we're going to use that definition, assuming we have two functions that both have a limit, L1 and L2. We're going to prove that f plus g has a limit L1 plus L2. And by the way, in this problem, L1 and L2 are just real numbers. They cannot be in R sharp because we don't know how to do addition of infinity, right? So we're not going to have that. Okay, perfect. So basically what I like to do is start with what I'm trying to prove and then use the assumptions as they become relevant to the problem. So to prove this limit here, what's the first line going to be?
Let epsilon greater than 0 be given.
Perfect. Let epsilon greater than 0 be given. Does that make sense to everybody? And of course, our job is to come up with this alpha over here. Okay? But we don't maybe know how to find it yet. What we do know are these two assumptions right here. Okay? So if we know these two assumptions and we have an epsilon that has been given to us, what could we already be able to do?
The absolute value of f of x
Minus
L1
L1
is less than epsilon, and absolute value of g x minus L2 is less than epsilon.
For which x's would that be true? For which x's would f of x minus L1 be less than epsilon and g of x minus L2 be less than epsilon? Is this true for all? So does this mean that for every x in the whole real numbers, absolute f of x minus L1 is less than epsilon? Look at our definition, right? What does it mean to say the limit is equal to something? It means that given any epsilon, there exists an alpha such that this is true. So what I would do for this first one is I would say from the assumption, there exists an alpha 1, let's say. Okay, so let's pick a preliminary alpha 1 such that there exists an alpha 1 such that if x is greater than alpha 1, then absolute f of x minus L1 is less than epsilon. Okay? There's a chair right over here. Okay? And then likewise, there exists an alpha 2. Okay, so similarly, there exists an alpha 2 greater than 0 such that if x is greater than alpha 2, absolute value of g of x minus L2 is less than epsilon. So we can make f of x very close to L1, and we can make g of x very close to L2. Okay? So based on that, what do you think would be the alpha that we would ultimately want to pick here?
It will be the maximum of alpha 1 and alpha 2.
Correct. You want the maximum. If you're ever wondering, should it be max or min, always choose the one that restricts the x's the most. Which one gives you the least a number of x's for which the assumption applies. So if alpha 1 is right here and alpha 2 is right here, then the alpha 1 condition applies to all of these x's, right? And the alpha 2 only applies to all of these x's. So this is the domain where you can, where both conditions will work. This is what you want to pick, the least x's that you can choose. So we're going to choose the max of alpha 1 with alpha 2. Okay? Does that make sense? Mm-hmm. Okay, and now we have to check that that alpha works. So I'm going to assume that x is greater than alpha. And I'm going to check that if I take absolute f of x plus g of x minus L1 plus L2, which I'm going to write this way. I'm going to just subtract the L1 and the L2 like that. I want to just check that that's less than epsilon. Okay. Do you guys think that this is going to work? If we think ahead, what would you want to do first to kind of simplify this? Or what would be a good first step?
Maybe we can have the absolute value of f of x minus L and
Minus
L1.
There we go. Let's put those together. Exactly. So this is going to be equals here. Okay, put those together and then put the other two together also, right? So I'll put g of x minus L2. I'll put all of that together. Does that look all right? Mm-hmm. Okay, good idea. Okay. So now what could I do?
then we're going to use the triangle inequality.
Very good. Triangle inequality. Great. So the triangle inequality gives me absolute f of x minus L1 plus absolute g of x minus L2. So perfect. We would do exactly that. Okay, and now, what do we do next?
We have this.
Remember, x is bigger than alpha, which means that it is bigger than alpha 1 and it is bigger than alpha 2. So x is big enough for which we can apply everything we've written down.
That's going to be less than or equal to epsilon.
Yeah.
So this one is going to give me
Epsilon.
epsilon, and this one's going to give me epsilon. So is this good?
No.
We want the whole thing less than epsilon. That's why I was asking you earlier, do you think this is going to work? It's not, so we have to fix something.
This one will be epsilon over 2.
Yeah.
Correct. This is what we need to fix. And that's okay if you don't see that right away. It's just when you go to write up the final parts of the proof, you want to be sure you're putting that in there. Okay, good. So then we come back over here and we say less than epsilon over 2 plus epsilon over 2, which is epsilon. And that's the end of the proof. Okay? So that is very nice. So this is an example of limits at infinity, right? We're doing an actual calculation of a limit that is going all the way to infinity. Okay, everybody comfortable with that one? Okay. Let me see what I want to do next here? Yes, okay, so let's go to this one. Can I erase anything yet? Are people still writing?
You can erase it.
You sure?
Yeah, I
Okay.
followed
You can take a picture as well.
No, I followed that part.
Okay, got it. Okay, so limits at infinity, we can do those. Let's take another example here. See how this one goes. So number 2. Okay. Prove if xn and yn are Cauchy sequences. Okay, say we take 2 Cauchy sequences, then so is xn times yn. Okay, so this is under multiplication, and if you multiply 2 Cauchy sequences together, you get another Cauchy sequence. This would be another probably 2-part question. The first part would really ask what is the definition of a Cauchy sequence. Excuse me, and then you would use that. We would use that to prove this thing. Thank you. Okay, so with that in mind, let's write down the definition of a Cauchy sequence first, so that we get that down. These kind of things are probably on those flashcards somewhere. So, so xn is Cauchy if, okay, do you guys, who knows the definition already?
For every epsilon greater than 0, there exists a delta greater than 0.
For every epsilon greater than 0, there exists a delta greater than 0 such that
if n not greater than n and m.
So actually, is this what you want here?
No, it's n not
Okay.
a natural number.
Okay, good. There we go. So let's fix this. There exists an n naught in the natural numbers.
Yeah.
That's better. Okay, such that
Such that if n is greater than n naught,
if n is greater than or equal to n naught, then
and the m is greater.
and m. Very good. There's an m and an n, two indices
Yeah.
greater than or equal to n naught. Then
xn minus xn less than epsilon, the absolute value.
great. Absolute difference xn minus xm is less than epsilon. Okay, I think we got that. Okay, so that's the definition. So we would like to prove that. So over here, I'm going to start writing the proof, and then we may need some scratch work at some point, so we'll use the middle for some scratch if we have to. What would be the first sentence of this proof?
Let epsilon greater than 0 be given.
Okay, all together in unison. We're getting used to that this semester, aren't we? So let epsilon greater than 0 be given. Great. So we have to come up with an n naught. Now, of course, xn and yn are already both Cauchy. So we can.
So there already exists n right?
So there already exists, and maybe I'll call it something else because our final n naught is going to come later. But at least for right now, there's an n1 and an n2 for these two sequences. Okay, good. So let's just say that right now. Then, by definition, there exists an n1 in the natural numbers such that n and m greater than or equal to n1 implies absolute xn minus xm less than epsilon. And there exists an n2 in the natural numbers, right? Such that if n and m are greater than or equal to n2, then it would be yn minus ym, the absolute difference of that, less than epsilon. Okay? You're just using the definition. Okay? And then, what am I going to want for my final value of n naught?
It will be the maximum of n1 and n2.
Okay, good. Let n naught be the max of n1 and n2. So far we're writing our whole proof here. Actually writing down the whole proof of this thing. So what we have to do is check that this n naught is correct. So we just assume that n and m are greater than or equal to n naught that we wrote down. And we're just going to check that that max is the right thing. Okay? which means we need to look at the absolute value of xn, yn minus xy. We need that to be less than epsilon. Okay. So now is where, so we have these two things that we can use, but at the moment this is what we have. So,
Can we add and subtract?
XY.
okay, we need to add and subtract something inside here. There's a little, you guys have seen me do this, right? So there's a little trick here. We leave x and y in like it is. I'm going to subtract xy over here just like it is. What would I put in the middle to add and subtract?
It would be
X and Y.
Well, x and y is what's right here. So if I add and subtract that, I don't want to add or subtract either of these two. It needs to be a little different.
X and Y.
X and
Hey, actually, hold on a second. This should actually be, there is no x or y here. Sorry, this should be xm and ym, right? And same thing over here. Let me fix that right now.
Okay.
Okay, that's a little bit better.
Yeah.
Okay, so what do you want me to put here now, Sal?
So it was X and
YM.
right.
X, N, Y,
M.
M. Okay, let's try that. And then we add X, N, Y, M right there as well. So we get those terms like that. Okay, great. Now what would you want me to do?
We grouped them and factor out.
Okay, are you happy with how they're grouped?
These
These two and then these two?
Yeah.
Okay. So, yeah, this is fine. So I can, in other words, what you're saying is I can factor xn from the first part. That leaves me yn minus ym. And then I can factor xn minus xm times ym right there. Okay. I don't have a lot of room here, but let's see if I can finish this up now. So what do I do next?
So we have yn minus ym less than epsilon, and we have.
Okay, but before I do that, there's still another step. I would have even done it before I did this step.
We're going to use triangle.
Yes, you need to be using the triangle inequality. That actually should be the high priority right now. So the triangle inequality says I can replace this with absolute xn times absolute yn minus ym. And this one is absolute xn minus xm times absolute ym. Okay, whoops, there should be another bar there. Okay, so that's what we have. We want this whole thing to be less than epsilon. I know that each of these pieces is less than epsilon, and I also know that I can change those if I want to any numbers that I want. So back up here, these epsilons, these are the same as what was given, but they don't have to be. Like on the last problem, we had to go back and change epsilon to epsilon over 2, right? Same thing here. We can change these if we want to, okay? But they do have to be changed to something that's a constant. You have to change them to something that's a constant. So let's think about this for a second. I'm going to get something out of my office real fast. Think about what we could put in there. So,
Can we go back up there
uh-huh.
to the one that you highlighted is triangle inequality? Oh no.
Don't think you want to because you have it the way you want it right here, right?
No, I'm thinking.
But we can change what this is.
Yeah. Because I'm thinking.
Oh,
of
I'm
the
saying you're
X-
thinking of this one.
Yeah.
So you could like get an upper bound on absolute xn,
Yeah.
but your upper bound will be in terms of xm, right?
Which won't work.
So we need to stop and think about Cauchy sequences again. Do we know anything about Cauchy sequences?
Yeah, converge.
They do converge in R. If they converge, then
They converge to.
like what else does that mean? If they converge, if a
They're
Cauchy sequence, they're bounded.
Yes.
They're bounded, which means that each of these absolute xn and absolute ym are actually bounded by something. So I actually need more room for this proof. I'm going to come over here. Okay, so what I'm going to do is, actually maybe what we'll do is, let's just do an insert into the proof. Instead of this, let's just do an insert. I'm going to do an insert over to here, just so I have the room for it. Okay, so since xn is bounded, since it is Cauchy, it is bounded. It is bounded. So what does that mean again? Like, how would we write that? If you have a Cauchy sequence, it is bounded. So how could we write that as a mathematical way of saying it?
There exists beta greater than 0 such that xn does not equal to beta.
Okay, the absolute value of the terms is less than or equal to some bound, right? So let me just call it B1, and this is for some real number bound B1, right? So we have that, and then what else do we have?
It has a supremum and infimum.
True. What else do I want to write down here? So I already know now that this one is going to be less than B1 right here. So actually, this yn minus ym, can we adjust our epsilon here to be something else that will, so that this, I'd really like this first term to end up being less than epsilon over 2. So what would I put here?
Maybe epsilon over 2 times b1.
That's it. That's it.
I thought I was wrong.
Oh, no, that's perfect. That's perfect. That's it, because now this one, you see, this is going to be less than or equal to b1 times epsilon over 2 b1, right? Okay, and then similarly here, oh, well, we need to go back and get the second one figured out. So what do we, so I need to come over here, and what else do I need to do?
Since yn, so you repeat it.
Yeah, so basically you just do the same thing again, right? Since yn is Cauchy, it is bounded. Okay, say the absolute value of yn is less than or equal to b2 for some b2 in R. And when we say that, we're talking about for all natural numbers. I should have been clear about this. For every natural number, absolute xn and yn are both bounded. Okay? If you prefer, you could go back now and do a max bound. You could like let b be the max of b1 and b2 and just use b everywhere. But you don't have to. You can get away with this just like this. Then I would just simply put right here, this would be, well, I have to fix this one now. I'm going to go back and fix this. What do I want to make this xn minus xm less than?
Epsilon over 2b2.
Good, epsilon over 2b2. So this becomes epsilon over 2b2 times b2, and all of that is epsilon. Okay? All of that becomes less than epsilon. Clear enough? All right, great. Perfect. Actually, this will be a strict inequality here because these are strict inequalities right there. So, okay. So that proves it. So that's the key thing to use that most people tend to forget about is you have to use the fact that Cauchy sequences are bounded. Okay. That's one of those things that's in your notes. It'd be worth reviewing how to prove that. Okay, that's something you might want to be able to do. You should be able, in the review packet, I kind of listed all of the main results from this section for the second midterm, and I sort of indicated on them that you should be able to prove those. Okay, I might ask you. I think on the sample test you're going to see that I actually did that. I just took a couple of results and I gave people a choice. I said either prove this one or this one.
There's like the
monotone convergence theorem and monotone subsequence theorem, and I gave people a choice on that. But I might do something like that again, where I ask you to prove something and maybe give you a choice about it. Okay. All right, so far so good. Let's do a few more things here. How about this one, number 3? Okay, this one is going to be asking you to give an example. So I will do that. Whenever you give an example, be sure that you explain the example. All the assumptions of the example, make sure I understand that those are justified. And then why the example works, basically. So give an example of a function, I'll call it f, that goes from r to r, such that f does not have a limit at any point C, so it does not have a limit, but absolute value of f has a limit at every C in R. Okay, there we go. So this is a function where every single element of the real numbers, the function's limit does not exist. And yet, after you take the absolute value of this function, suddenly it has a limit at every point of the real numbers. So let's quietly think about it for a minute or so and give everybody a chance to think what kind of function they could use for this. Because the key thing here is getting the function right. Once you get the function, showing all the steps will be pretty easy. Pretty easy. Let's think about this. Obviously, you have to make a function that changes drastically when you take the absolute value. So your function had better have some negative values. If your function is always positive, then taking the absolute value of that is just going to stay the same. It's not going to change it. So you need a function that has some negative values. But you don't want them to all be negative, because if all of your values were negative, then the negative of f would be all positive, right? And so then, again, taking the absolute value of that would do nothing to that function, right? So you need to have some positives and some negatives in terms of what this function is. Just sitting down to rest my foot for a minute. He told me to get off my feet every so often for 5 minutes. Anybody have any thoughts how to do this?
Negative 1 and positive 1.
Okay, a 1 and a minus 1. The nice thing about that is, when you take the absolute value of this function, it will become a constant function. And that will definitely have a limit. So the second part will be good, right? The absolute value of f will have a limit at every point, because it's just the line y equals 1, okay? So this is what you meant, right? A piecewise defined function? Okay, so then the next question would be, this is exactly right. The next question would be, how do you make your pieces?
Is this the first part that when x is greater than or equal to 1?
Greater than or equal to 1.
And where x is less than 1.
Okay, let's look at that. Let's see what that does. If I draw the graph, here's my x-axis, my y-axis. The pictures are good, right?
Yeah.
So the function, you're saying, so here's 1 and minus 1 and minus 1. So you're saying if x is greater than or equal to 1, the graph is going to look like that. And if x is less than 1, it's going to look like that. So, of course, when you take the absolute value of the function, it will just be equal to 1 all the time, and that'll be good. The limit will definitely exist. Is it true that right now that this function does not have a limit at any point?
Yeah. So any point that means just like if we pick
Over
2,
here,
right?
yeah.
Or
Does the limit exist right here?
Yeah.
Yeah.
It does, right? It's right at that point. Okay, so this function doesn't quite work. I like the thought. I like this thought, 1 and minus 1, but we need to do it a little bit differently.
So it has to be kind of
Maybe odd and
alternating.
even?
It needs to kind of alternate a little
Yeah,
bit.
odd and even.
Well, odd and even would be great for
Yeah.
sequences. Like we had like plugging in 1, 2, 3, 4, 5. But this is like all the x-axis of real numbers.
The problem will be when we have like decimals and rationals and irrationals.
Oh, you're getting there. You're talking yourself into what the right answer should be right away. I'm hearing the words I want to hear. Yeah, so we can't just do odd and even, because that's only just like different dots, along the axis. So we need to have something that's fluid, that goes all the way across the x-axis. So do we think we have